In this section, we're going to be going over inverse trig functions. So remember back to when we were evaluating trig functions at reference angles, we discussed this table right here. As long as you know this table going into some of these questions, that's going to be about half the battle. So we're going to be covering the inverse trig functions for sine, cosine, and tangent. Cosecant, secant, and cotangent also have inverse functions. We're just not going to be looking at them in this section. So basically, as long as you have this table memorized for this section right here, then we should be good to get started with most of these questions. So starting off here, let's take a look at the inverse sine function. So just to remember some of the properties of inverse functions, in order for a function to actually have an inverse function, it has to pass the horizontal line test. So if we take a look at the graph of sine, this is just our normal function y equals sine of x. This fails the horizontal line test. Any horizontal line is going to intersect the curve, technically in an infinite amount of spots. So as this is, sine fails the horizontal line test, meaning it does not have an inverse function, but we want it to have an inverse function. So what we actually do, in order for it to pass the horizontal line test, we restrict the domain from negative pi over 2 to positive pi over 2. So basically what we're doing is pretending like sine only exists from negative pi over 2 to pi over 2, which is that little sliver of the function between those two values. If it only exists on this little interval right in here, then it does pass the horizontal line test, meaning it will have an inverse function. So thinking back to a couple other properties of inverse functions, in order to actually see the graph of an inverse function, we're going to take our function and reflect it over the line y equals x. So if we took this little sliver of our sine function and reflected it over the line y equals x, right? This is like the little line y equals x. That would give us the graph of the inverse function, which we'll see on the next page. Another last property that's going to be very, very important when we start to answer some of these questions in a little bit is inverse functions have flipped ordered pairs. That means if we have the point 2, -3 for our function, then the point -3, 2, flip the ordered pair, is on the graph of the inverse function. So once again, just recapping a couple inverse function properties. In order for a function to have an inverse function, it has to pass the horizontal line test. In this case, we had to restrict the domain for sine. In order to determine the graph of the inverse function, we have to reflect it over the line y equals x. And inverse functions have flipped domain and ranges, meaning flipped ordered pairs. So taking a look a little bit more in detail with the inverse sine function and the notation and its graph. So we have two separate notations for how we denote the inverse sine function. We can either use the one on the left here, you can call it inverse notation. Don't you read that as sine inverse. So this is sine inverse. Even though that is a -1, it looks like a -1 exponent, right? That is not what it is. This is not sine to the -1. You just read this as sine inverse, so it's kind of dumb notation, in my opinion, because it looks like an exponent, but it's actually not. The one on the right, you would read this as arc sine of x, and they both just mean the same exact thing. They both represent the inverse sine function. So taking a look back real quick at the previous page, if we took this little sliver of sine of x from negative pi over 2 to pi over 2, and if we reflected that portion over the line y equals x, it would actually look like this graph right here on the right. So another thing, remember what we just said with inverse functions, they have flip-flopped domain and ranges. Notice that we have the restricted domain, negative pi over 2 to pi over 2, and the range is still -1 to +1. That's going to be the complete opposite for the inverse function over here on the right. The range of the inverse function is negative pi over 2 to pi over 2, and the domain is negative 1 to 1. So inverse functions completely flipped domain and ranges. So think back to when we talked about logarithms and exponential expressions and how they're related. We're going to do something a little bit similar. So for example, let's say we have just y equals sine inverse of x. We're going to be able to convert between sine inverse and sine form. Y equals sine inverse of x is essentially the same as sine of y equals x. So notice where the variables x and y are. These equations or these forms are essentially they mean the same thing. They're just in two separate forms. So one really important distinction here is that the inverse, which is obviously the way I have this written right here on the left, this is sine inverse. This is not the same thing as 1 over sine of x. This is the reciprocal. And we know the reciprocal of sine is cosecant. So long story short, the inverse and the reciprocal are not the same thing. Those words are not interchangeable. So just make sure you know the difference. So what we're actually going to be doing here is we're going to be evaluating sine inverse of a certain value. So for example, before we see we're going to do this, let's take a look at the next page. For example, we're going to evaluate sine inverse of radical 2 over 2 without using a calculator. So when we're trying to evaluate sine inverse of some value, what's important to remember first and foremost is that sine inverse of a value, we're going to think of that as an angle. So sine inverse of some value is going to be an angle. So we're going to rewrite it at first as sine inverse of whatever that value is equals some angle theta. And then we're going to use the format that I have written above, and we're going to rewrite it in terms of sine. So instead of theta equals sine inverse of x, we're going to rewrite that as sine of theta equals x. And the one little tricky part here is the angle that this is referring to has to be on the restricted domain that we discussed on the previous page. The restricted domain for sine was negative pi over 2 to pi over 2, including those endpoints. So long story short, what we're going to be doing here is letting our original question be some angle. We're going to rewrite it in terms of sine because I think it's a little bit easier to think of it in terms of sine rather than the inverse. And we're going to ask ourselves, sine of what angle will give us this value right here, such that this angle is between negative pi over 2 and pi over 2. So something that you can do if you want to, you can memorize this little table if you really want to. I'm not going to do it this way. The only thing you have to memorize is that reference angle table from the first page, which once again, we already should have this memorized. So as long as you have these values memorized for sine, then these questions are usually really quick and easy. So let's just jump into an example so we can see what the heck, how the heck to do these questions. So find the exact values of the following. Once again, we're doing these by hand. We're not doing these in the calculator. Sine inverse of radical 2 over 2. So something you're going to notice for all of these questions on this page, and when we do cosine inverse and tangent inverse, is that all of these input values are going to be positive for now. We'll deal with the negative ones separately afterwards. So the reason why if that input is positive, why it's a little bit easier is because as soon as you see that that's a positive input, the answer is a reference angle, so you should have the answer just memorized. So I'm going to do this first one the long way, and I'm going to do the next ones a little bit quicker. So what we can do, just using the technique from the previous page, if you like to do it this way, the answer is an angle. So you can say that this equals some angle theta, and then you can convert this to the other form and say this is the same as saying sine of what angle equals radical 2 over 2. So if you write it like this, what you're trying to do is figure out what is the angle, sine of what angle equals radical 2 over 2, such that that angle is a reference angle. So we know that sine of pi over 4, right? Pi over 4 is the reference angle for sine. That gives us radical 2 over 2. We know that sine of pi over 4 is radical 2 over 2. So that means that's our answer. Pi over 4 is the answer. That means sine inverse of radical 2 over 2 is pi over 4. So this is kind of like the long drawn out way that I just kind of set this up. You can probably tell though that once you see one of these questions, you can probably skip directly to the answer if you just think about it in your head. Sine inverse of radical 2 over 2, that just means sine of what reference angle equals radical 2 over 2, and then you know that answer is pi over 4. So you actually don't have to show any work for a lot of these questions. You should be able to just skip to the answer right away once you get comfortable with them. So let's see the next one, arc sine of 1/2. And remember, arc sine, sine inverse, same thing. So I'm going to set this one up a little bit differently, just a little bit shorter than the other one. What this means is we're trying to figure out sine of what angle. I'm just going to put a question mark for now, I guess. Sine of what angle equals 1/2. And then since this is a positive 1/2, we know that our answer is a reference angle. So we know that when we're looking at reference angles, sine of pi over 6 equals 1/2. So that means arc sine of 1/2 is pi over 6. So basically we're just using the property of inverse functions where they have flipped x and y coordinates. And that's literally all we're doing. We're just essentially thinking backwards here. So next one, sine inverse of radical 3 over 2. I'm going to set this one up the same way I just did it. What we're doing is saying sine of what angle equals radical 3 over 2. And since this is a positive radical 3 over 2, that means the answer is a reference angle. We know that sine of pi over 3 is radical 3 over 2. So sine inverse of radical 3 over 2 is just pi over 3. So once again, just thinking backwards, the answer to these inverse questions are going to be angles. Also notice that I'm putting these answers in radians. So you should basically always have these answers in radians unless the question asks you specifically for degrees. So next one, sine inverse of 0. So sine inverse of 0, we say to ourselves, sine of what angle equals 0? And we could, even though technically speaking, 0 is not a reference angle, but we do have it on our little reference angle table. So if we have our reference angle table memorized, we know that sine of 0 equals 0. So our answer here is 0. Sine inverse of 0 equals 0 because sine of 0 equals 0. And then for the last one, where this starts to get a little bit trickier, when we were evaluating just plain old sine and cosine of some angle, sine and cosine both have domains, negative infinity to infinity. So we never had to worry about any weird domain errors. But when we look at sine inverse of 4, for example, so 4, just take a look at the reference angle table on this first page of notes here. Notice that all of our inputs are these values here this time, right? Sine inverse of 0, 1/2, radical 2 over 2, and so on. And then our answers are the radian measurements over here on the left. So sine inverse of 4, there's no value of 4 in this table. So basically one of two things happens. If it's not one of these values that are already in the table, then either we just don't have it memorized and we would have to use the calculator, or it does not exist. So let's see what happens with sine inverse of 4. Let's try to think backwards. Sine inverse of 4 means sine of what angle equals 4. So there's two ways to think about this right now. You can think about it using sine inverse or regular sine. Let's look at regular sine over here on the right. We know that the range of sine is, and this is for sine, the range of sine is -1 to +1. So sine will never equal 4, right? Sine will always give you an output value between -1 and +1. It'll never actually reach an output value of 4. So for that reason, this answer just does not exist. So you can always, I always recommend thinking about it in terms of the original functions. I think it's easier. You could also think about this where the domain of sine inverse is between -1 and 1. It means the same exact thing. Either way, the answer here does not exist, or you can write is undefined. So does not exist or undefined are both acceptable answers. So if you try to plug this in the calculator and put sine inverse of 4, the calculator would say domain error because 4 is outside the domain of sine inverse, or you can think of it as 4 is outside the range of normal sine. So that's where you do have to be a little bit careful with these inverse questions. Right, so let's do the same exact thing with cosine inverse. And once again, if you're comfortable with that table from the first page, this hopefully should not be that bad. So just like the sine function, cosine super fails the horizontal line test, right? So this is the graph of cosine. So if you put a horizontal line anywhere in this graph, it's going to fail the horizontal line test because it's going to intersect it more than once. So just the way that it does not have an inverse function. We need it to have an inverse function to answer questions. So we're going to restrict the domain from 0 to pi. So the restricted domain for sine was -pi/2 to pi/2. The restricted domain for cosine is 0 to pi. So when we consider questions with the inverse cosine, we're only thinking about cosine on this little sliver between 0 and pi. So just like for sine inverse that we did a few pages ago, cosine inverse, if we want the graph, we're going to reflect this over the diagonal line y equals x. We're going to flip the domain and the range. So instead of the domain being from 0 to pi, that's going to be the range of the inverse. So over here on the right, you can see the graph of cosine inverse. The range is from 0 to pi, and the domain of the inverse, -1 to 1, is the range of cosine. And then this is just what the graph looks like if you reflect it over the line y equals x. So just like before, same type of notation. We have cosine inverse of x using a little -1 superscript, not an exponent, that's just the inverse notation. Or we can write this as our cosine. They both mean the same thing. So we're going to be answering the same type of questions here, and we're going to be doing the same little process in the beginning, where if we end up seeing y equals cosine inverse of x, it's usually, in my opinion, a lot easier to think of it in terms of cosine. So we can think of this as cosine of y equals x. So we're just going to be basically doing backwards thinking in terms of cosine, just because we're used to probably thinking in terms of cosine rather than the inverse. And then, of course, once again, cosine inverse is not the same as the reciprocal, so don't get those two confused. They are not the same. All right, so like I said, what we're going to be doing is essentially the same thing we were just doing with sine inverse. We're going to be evaluating cosine inverse of some value. So, for example, cosine inverse of 1/2, arc cosine of radical 3/2, and so on. We're basically going to be following the same steps. We're going to know that this represents an angle. So once again, our answers are going to be angles in radians. So we can let it equal theta. Then we can rewrite theta equals cosine inverse of x as cosine of theta equals x. And we just have to remember that the theta that we're trying to figure out is going to be on the restricted domain of cosine between 0 and pi. So I do have this little table here again. If you'd like to memorize stuff, you can memorize this, make it a little bit easier. I don't like memorizing things, so I'm not even going to refer back to this table. All we have to do once again is know that reference angle table from the first page of notes from today. So let's just jump into a question just so we can see how to do this. Cosine inverse of 1/2. So also notice that all of these values are either going to be positive or 0, technically. And just like before, as long as it is a positive value, the answer will be a reference angle, so we should have it memorized. Technically, like we saw with sine inverse of 4 a couple pages ago, the answer might not exist, but we'll worry about that when we get to the last one of these examples and a few examples here. So cosine inverse of 1/2. So once again, if you like to show all of your work here, we know that the answer is an angle. It's going to be a reference angle because it is a positive 1/2. We can rewrite this, if you like to think of it like this, as cosine of theta equals 1/2. And then we're asking ourselves, cosine of what reference angle equals 1/2? So just thinking backwards a little bit, we know that cosine of pi over 3 equals 1/2. And then we're just done because that means pi over 3 is the answer. So cosine inverse of 1/2 is pi over 3 because cosine of pi over 3 equals 1/2. So now for the remaining couple for this one, I'm going to do what I did like with sine inverse. I'm going to go a little bit quicker, maybe not show all the work. Arc cosine of radical 3 over 2. So arc cosine, cosine inverse, same thing. So we're going to ask ourselves, cosine of what reference angle equals radical 3 over 2? And then we know that cosine of pi over 6 is radical 3 over 2. So that means our answer is pi over 6. So if you're comfortable and you have these values memorized in your head, you don't even have to write this little chunk out over here on the right. So for the next one, cosine inverse of 1. So this one might be a little bit harder, but once again, if you have the table memorized, the little reference angle table memorized, it's not that bad. So we ask ourselves, cosine of what angle that's on the reference angle table equals 1. So if you look at that reference angle table from the first page, we'll see that cosine of 0 equals 1. So that means cosine inverse of 1 equals 0. So if you know this stuff, very quick and easy. If you don't, it's going to be pretty hard just to guess to get these correct. So let's see one more, cosine inverse of 3 over 2. At first, this might seem like the one that we did 2 examples ago. Radical 3 over 2 was the input, except this is 3 over 2. 3 over 2 is not one of those values. Let me scroll back to that first page. 3 over 2 is not one of these values that are inside of the reference angle table for cosine. So what that means, once again, is one of two things. Either the answer does not exist, or we have to use a calculator because it's something that we just don't have memorized. Let me scroll back and find it real quick. There you are. So cosine inverse of 3 over 2. I'm going to go ahead and write it like this again. Cosine of what angle, question mark, equals 3 over 2. So just like sine, the range of cosine is only -1 to 1. So 3 over 2 is 1.5. 1.5 is not between -1 and 1. So since 3 over 2 is out of the range of cosine or out of the domain of cosine inverse, this does not exist. Or you can write is undefined. Either one of those are completely fine. So once again, if you plug this in the calculator, cosine inverse of 3 over 2, you're going to get a domain error, meaning the answer does not exist. All right, so let's see one more of these, and then we'll discuss a small issue that we might see, and then we'll answer a couple word problems. So the inverse tangent function. So once again, for the third time in a row here, tangent, here's the graph of tangent. It super fails the horizontal line test because it intersects the graph an infinite number of times. Any horizontal line will intersect it an infinite number of times. So at first glance, we would say that it does not have an inverse function, but we need it to in order to answer questions. So we're going to restrict the domain from negative pi over 2 to pi over 2. So what's actually nice about this is almost the same as the restricted domain of sine, right? The only difference is that since tangent has vertical asymptotes at negative pi over 2 and pi over 2, we do not include those because of the vertical asymptotes. So it's almost the same restricted domain as sine, except we don't include these endpoints for tangent. So for the third time, once again, in order to get the graph of tangent inverse, we're going to flip the domain and the range. We're going to reflect this curve over the line y equals x. So basically, instead of the domain being negative pi over 2 to pi over 2, and the range being negative infinity to infinity, we're going to flip it. And now the graph of tangent inverse has a range of negative pi over 2 to pi over 2 and a domain of negative infinity to infinity. So you can see that as long as you know properties of inverse functions in general, trig inverse questions in the graphs aren't anything overly complicated. So we have the same notation, tan inverse of x or arctangent of x mean the same thing. And we're going to be doing the same type of questions where if we have something like tan inverse of x, it's usually, in my opinion, easier to think of it in terms of tangent. So y equals tan inverse of x is the same as tangent of y equals x. So I have the same setup again, just like the other ones. Make sure you remember that the inverse is not the same as the reciprocal. And we're going to be answering questions using literally the same exact techniques. So we're going to be answering questions, what is tan inverse of some value? The answer, once again, is an angle. If you want to think of it in terms of tangent, that's how I usually recommend thinking of it in terms of your head. And then the angle that we're trying to think of for the answer is going to be on the restricted domain for tangent, negative pi over 2 to pi over 2. I have this little shortcut table written down here if you like to memorize stuff, but I'm not going to bother using that. Once again, we're just going to know the table from the first page of notes, and that'll be enough to get us through these questions. So first one, find the exact value of tan inverse of radical 3. So let's do this one a little bit quicker. You could set it up the way I've been setting up the first ones for sine and cosine inverse. But now we know that since this is positive, the answer is a reference angle, so we should have this memorized. So let's just scroll in case anybody's having difficulty here. Let me scroll back to the first page. And we wanted to know what is tan inverse of radical 3. So here's tangent, here's radical 3. That means pi over 3 is the answer. So if I were you guys and you were taking an exam or something, I would get the exam and I would actually just write this table down, because if you have it in front of you, you don't have to really think too hard. The answers are just looking straight at you. So tan inverse of radical 3 is pi over 3 because tangent of pi over 3 is radical 3. So we know the answer here is pi over 3. And that's all you need. You don't need to show any work for this one. But if you want to just write down a little reasoning, that's because tangent of pi over 3 equals radical 3. All right, next one, arctan of 1. So we ask ourselves, tangent of what reference angle equals 1? And this is actually going to be pi over 4. So we know that tangent of pi over 4 equals 1. So arctangent of 1 is pi over 4. Next one, tan inverse of 0. So this one, once again, 0 can be usually a little bit trickier, but if you write down the reference angle table for yourself, it's a lot easier because the answer is looking at you in the face. we ask ourselves tangent of what angle equals 0? So tangent of 0 equals 0. So that means tan inverse of 0 is 0. So for this one, even though these are both 0, tangent of 0 equals 0, tan inverse of 0 equals 0, technically the 0 answer that we're referring to is the input value of tangent for the format on the right. Right, so yeah, pretty much we're doing the inverses of all of the inputs in that reference angle table. Everything we've seen was pretty straightforward because all of our answers were the angles directly on the reference angle table. So now for the part where it's a little bit trickier, but as long as we use symmetry to answer these questions, it's not going to be as bad as what you're looking at on the page right now. So the question is, what if the input is negative? So for example, the questions we're going to be answering, sine inverse of negative 1/2, negative cosine inverse of negative radical 3/2, tan inverse of negative 1. What happens when those inputs for these inverses are negative? What we're going to do, let's take a look at, before we see the examples, and we'll look at sine inverse and tangent inverse together. The reason I'm looking at sine and tangent inverse together is because they have the same type of symmetry, and we restrict the domains over the same interval. So sine and tangent are both odd functions, and we restrict them both from negative pi/2 to pi/2, right? So if we're evaluating, taking a look at sine inverse on the left, sine inverse of a negative, all we have to do is first evaluate it as if it's positive, sine inverse of the positive answer, and then negate the answer. So sine inverse of negative x is the same as negative sine inverse of positive x, and that's the same thing for tangent over here on the right. Tan inverse of negative x equals negative tan inverse of positive x. So basically all that means is if you negate the input value, then the answer is going to be the negative output value. So negate the x, then you negate the y. Negate the x, negate the y, negate the input, negate the output. So let's see some examples. Let's take a look over here on the left. Sorry for kind of squishing this all in. Let's take a look at sine inverse of 1/2. So you're probably saying to yourself, that is a positive value, which is true. So based on what we were doing before, we should know that this answer is pi/6, right? Sine inverse of 1/2 is pi/6 because sine of pi/6 equals 1/2. So since 1/2 was positive, we knew pi/6, the reference angle, was the answer. So the reason I did this one, even though it was already positive and we already did this, is because we can now compare sine inverse of 1/2 with sine inverse of negative 1/2. So the great thing is here is as soon as you see a negative, what I like to do here is if it's for sine inverse or tangent inverse, ignore the negative. So first evaluate sine inverse of 1/2. We just said sine inverse of 1/2 was pi/6. And then since this is a negative input, we just negate the output, negate the answer, and then we're done. So I wanted to do these questions right next to each other just so we can see the similarities. Sine inverse of 1/2 is pi/6. So that means sine inverse of negative 1/2 is negative pi/6. So once again, even if you don't have the positive answer right in front of you, just pretend that the question is asking for the positive input first, and then just negate the answer afterwards. So before we see another example with sine, let's just see the reasoning for why this is, looking at the graph of sine of x on the restricted domain negative pi/2 to pi/2. So for sine inverse of 1/2, basically taking a look and relating this back to the graph of sine, what this means is that we need to have pi/6. Let's put pi/6 right here. That means sine of pi/6 this isn't drawn to scale perfectly, is 1/2, right? So sine of pi over 6 equals 1/2. Looking at this symmetry, it probably becomes a little bit more obvious that sine of negative pi over 6 is negative 1/2, which is the reason why sine inverse of negative 1/2 is negative pi over 6. So you don't need to be able to always draw the graphs out and think about things graphically. I think it's a lot easier if you can at least imagine it graphically, just so you get a nice symmetry reasoning for why this is the way that it is. Right, so let's see another one where we don't have any like clues for how to answer this. Sine inverse of negative radical 2 over 2. So as soon as you see it as a negative for sine or tangent inverse, we're going to ignore the negative. We know that sine inverse of radical 2 over 2 is pi over 4, because sine of pi over 4 is radical 2 over 2. And then since this is a negative input, you just negate the output, and then you're done. So basically, for sine inverse or tangent inverse, which we'll see in a second, if you have a negative input, your answer is just going to be negative, and that's literally it. So that's just a really small little trick where if you know it, once again, these questions will be very quick to answer and won't really pose any real issues. So let's do the same exact thing now for tangent over here on the right. Like we said, tangent and sine have the same symmetry. So we're actually going to do this the same exact way. So first one, let's say we want to figure out what is tan inverse of positive 1. So this is obviously positive. So we know the answer is a reference angle. Tan inverse of 1 is going to be pi over 4, because tangent of pi over 4 equals 1. So let's take a look once again, just like we did for sine inverse. Let's now compare this to tan inverse of negative 1. So obviously these are almost the same. Tan inverse of 1, tan inverse of negative 1. We do this the same as sine inverse. We just recognize that it is a negative. We ignore the negative. We already said tan inverse of 1 is pi over 4. And now we recognize that since the input is negative, so is the answer. And we get negative pi over 4 as the result. So we do we do the tangent inverse questions the same way that we do the sine inverse. If we have a negative input, you just negate the answer. So let's look at one more with tan inverse without any clues. Tan inverse of negative radical 3 over 3. So as soon as you see this negative, we ignore the negative for sine or tangent inverse. We know that tan inverse of radical 3 over 3 is pi over 6. And then we recognize since we had a negative input, we negate the answer, and then we're done. So tan inverse of negative radical 3 over 3 is just negative pi over 6. So once again, if you know this same little trick for sine inverse and tangent inverse, the questions are very, very quick. So the issue is the one that's left, and that's going to be cosine. So looking at cosine, looking at the graph, you can see that we have a different restricted domain for cosine, right? The restricted domain of cosine is 0 to pi. So we're not going to be able to use this same technique for cosine inverse as we do for sine and tangent inverse. So what we're going to do, just like I have highlighted right up here at the top, is if we are evaluating cosine inverse of a negative, we're always going to do pi minus the answer as if it was positive. So I'll show us why that is graphically once we do two of these questions here. But let's go ahead and just jump right in. So first one, let's take a look at something we've already done. Cosine inverse of radical 3 over 2. So radical 3 over 2 is positive. So right away we know the answer is a reference angle. We know that cosine of pi over 6 is radical 3 over 2. So cosine inverse of radical 3 over 2 is pi over 6. Let's just draw this out right now on the graph. So this is the graph of cosine, not the inverse. So cosine of pi over 6, not drawn to scale once again, is radical 3 over 2. So that's just what that kind of means graphically. Now let's look at the next one. Cosine inverse of negative radical 3 over 2. So they're almost the same. One's positive, one's negative. So the trick here, the common mistake, a lot of people just will put negative pi over 6. This is not how you do this for cosine inverse. Sine inverse, tangent inverse, if it's a negative input, negate the answer. That is not true for cosine inverse. What we have to do here is we're always going to do, based on what I have written and highlighted right up here, it's pi minus the answer as if it's positive. So this is just going to be pi minus pi over 6. So pi minus pi over 6, get common denominators. 6 pi over 6 minus pi over 6 gives us 5 pi over 6. So cosine inverse of a negative is always going to, in my opinion, it's always going to be the one that's the hardest for these inverse questions. So let's just see why that is. So we have, let's take a look at the graph. We have cosine inverse of negative radical 3 over 2, and we got 5 pi over 6. So if we scroll up here, basically what we're trying to figure out is what this answer is right here, such that it gives us an output of negative radical 3 over 2, right? So the reason why we have to do this weird pi minus for these questions is because graphically, this distance right here on the left is the same as this distance right here on the right. So on the left, we can see that that distance is pi over 6, right? 0 to pi over 6 is a distance of pi over 6. So that means this distance right here on the right is also pi over 6. So if we want to get from pi back to whatever this value is right here, we have to subtract pi over 6 from pi. So that's why we're always doing pi minus for cosine of a negative, because we have to start at pi and then subtract the answer, the reference angle answer. So let's see another one. Hopefully it makes a little bit more sense. Cosine inverse of negative 1/2. So what I like to do for these is, as soon as you see cosine inverse of a negative, just right away put pi minus. Cosine inverse of a negative, put pi minus right away. And then we're just going to evaluate cosine inverse as if it's positive. Cosine inverse of positive 1/2 is pi over 3. Get common denominators, 3 pi over 3 minus pi over 3. And we get 2 pi over 3. If you like to write out the whole entire thing, it would be pi minus cosine inverse of 1/2. I just like to skip to the step that I wrote, but that's up to you. So once again, when you're looking at these questions, think about sine inverse and tangent inverse of a negative the same way. You just negate the answer and then you're done. But then unfortunately, cosine inverse of the negative is pi minus the answer as if it was positive. All right, so two more kind of little concepts to get through here. Sometimes we have to use a calculator to evaluate trig functions or inverse trig functions in general, because we don't have everything memorized, right? So let's say we're trying to evaluate sine inverse of 0.3. 0.3 is not one of those values inside of the reference angle table. So this is not an answer that we have memorized. 0.3 is between -1 and 1. So the answer does exist. And we just know, we're told to use a calculator. So basically, just plug this in the calculator. Just make sure you are in radian mode, because once again, we always want the answers, these angle answers, in radians, unless it specifies that we want the answer in degrees. So if you plug this in the calculator, you just have to click the little second button and then click sine, because that'll give you sine inverse. So click second, sine, that'll show up as sine inverse. Sine inverse of 0.3. I'm going to round this. It says round it to the nearest hundredth. So I'm just going to put approximately 0.30, I believe, if you type this in the calculator. So just kind of a real quick little side note. This isn't super important for the concept of this class. Notice that this is actually the same, right? We rounded, but we had sine inverse of 0.3, and we got 0.3 as an answer. So we actually got the same input. We got the same answer as the input. For those of you that have taken a physics or might be taking physics, you might get to a point where you are dealing with some formulas or equations where you have sine of x or sine of whatever in your formula, and it simplifies really nicely to just whatever the input is. So you might see in a physics class that you can actually, instead of using sine of x, you can just use x itself in your formula only when x is small. So just kind of a real quick side note for those of you interested in taking physics or going to be taking physics, you might see that instead of using sine of x, if you know x is really small, sine of x is approximately just equal to x as long as x is small. So we knew the answer was going to be about 0.3 because 0.3 is small with quotes. Right, so let's see the next one, arc cosine of -1/3. Once again, this might look like something that we can do in our head, but -1/3 is not one of the values on the reference angle table, inside the reference angle table. So just plug this in the calculator, just practice doing it to make sure you can do it. Plug this in the calculator. I'm going to round this to the nearest hundredth. We get about 1.91 radians. And then for the last one, tan inverse of 100. At first glance, you might say to yourself, 100 is not between -1 and 1, but that's only something you have to worry about for sine inverse and cosine inverse. The domain of tangent inverse is -infinity to infinity. Either way, plug this in the calculator, and we get about 1.56. So nothing crazy, just wanted to make sure that, we can get some calculator practice, so make sure you're getting the same answers. So now for the last kind of main thing for this section is solving for angles and triangles and word problems. So in order to do this is thinking back to maybe stuff that we did in chapter 5.2, I guess, like right triangle trig. Now we're going to be not using the Pythagorean theorem necessarily, but we're going to be using right triangle trig with our, SOHCAHTOA, sine equals opposite over hypotenuse and all of that stuff, and then using inverse properties to actually find the angle in the triangle. So I'm only going to do one of each of these just for time's sake. So for this one, solve for angle in radians. So here's the angle we're looking for. And we have this side right here is radical 2. And this side is 2. So when we're trying to solve for the angle, we need to consider what sides are given, opposite, adjacent, or hypotenuse. We are given the hypotenuse and the adjacent side. So between sine, cosine, and tangent, which one deals with adjacent and hypotenuse? That's going to be cosine. So we can say that cosine of theta equals adjacent, which is radical 2, over hypotenuse, which is 2. And if we want to solve for theta in radians, we just need to ask ourselves, cosine of what reference angle equals radical 2 over 2? We can actually do this one in our head. We know that cosine of pi over 4 is radical 2 over 2. So this is just one that we could do in our head. If you wanted to plug this in the calculator, sometimes you just have to plug them in the calculator. If you plugged it in the calculator, let me actually set this up a little bit differently here. We would say theta equals cosine inverse of radical 2 over 2. So if you did not know this answer in your head, you would have to plug in cosine inverse of radical 2 over 2 in the calculator. And then the calculator, you would have to round. I rounded this to the nearest hundredth. We would get about 0.79. Okay, so maybe practice the other one right here and check the notes for the answer. Let's take a look at one more of these, and then we'll do maybe 2 to word problems. So let's now solve for the angle in degrees and round to the nearest degree. So this is the angle that we are looking for. We're given this side is 10, this side is 20. So we are given the opposite side and the adjacent side. So as soon as we know that we're working with opposite and adjacent, we should be thinking tangent. So tangent of opposite over adjacent, tangent of 1 or 10 over 20. If you wanted to, you could simplify this to 1 over 2, right? You don't have to. The only reason you might want to try is because now you ask yourself, can you actually do this in your head? We can't do this in our head. Tangent of what angle is 1/2. This is not one of those nice values on the reference angle table. So we're going to actually have to plug this in the calculator. And we're going to say this is equal to tan inverse of 1/2. Just make sure you're in degree mode, round to the nearest degree. So plug this in the calculator, round to the nearest degree, and we get about 27 degrees. All right, hopefully not too bad for that one. Once again, I'll skip this next one. If you want to get some more practice with this, take a look at that one in the notes. And let's take a look at a few more questions, a few more word problems. So a building is 50 feet high. At a distance away from the building, an observer notices that the angle of elevation to the top of the building is 41 degrees. To the nearest foot, how far is the observer from the base of the building? And we're going to round the answer to the nearest foot. So anytime you have a word problem, just start by drawing a picture. So we have a building, and then we have an observer standing some distance away. And we already know, let's start labeling things. We know the building is 50 feet high. So we also see that from the observer, the angle of elevation to the top of the building is 41 degrees. So from the observer to the top of the building, the angle of elevation, which is going to be this little part right in here, this angle, is 41 degrees. And then we want to know how far is the observer from the base of the building. So as you draw the picture, you should recognize that you're creating this right triangle. And I'm going to label what we're looking for. We're looking for that horizontal distance from the observer to the base of the building. So we should always have three things written down. We should have two numbers written down and then one variable. So it looks like based on where this angle is, we have the adjacent side and the opposite. So we know that we have to work with tangent. So tangent of, instead of tangent of just theta, we actually have the angle. So tangent of 41 degrees equals the adjacent side over the opposite. So these questions get a little bit trickier because sometimes you might be looking for a side, sometimes you might be looking for the angle. This time we're looking for the side. All we have to do here is multiply both sides by 50. 50 times tangent of 41 degrees. I just like to write the variable on the left side of the equal sign. And then we just have to plug that in the calculator. Make sure you're in degree mode. So 50 times tangent of 41 degrees. Round this to the nearest foot. We get about 58 feet. And then we're done. So just always make sure your answer makes sense. Based on the values that we have, does it seem like 58 makes sense? And yeah, it seems like 58 kind of makes sense based on the fact that this value is 50, the angle's 41. We didn't get some ridiculously small or ridiculously large answer. So I'll skip the middle one. If you want to see the middle one, take a look in the notes. Let's take a look at this one right here. A ladder leans against a brick wall. The foot of the ladder is 6 feet from the wall. The ladder reaches a height of 15 feet on the wall, and we want to find to the nearest degree the angle the ladder makes with the wall. So let's draw a picture. So here is a wall that looks just like my building. Here is a ladder. And already you can see how this is forming a right angle, triangle, right? So I'm even just going to fill this in. We have our right triangle right here. And we have that the foot of the ladder is 6 feet from the wall. So you have to make sure you always read this stuff twice. 6 feet from the wall for the foot of the ladder, that means that this length for the horizontal length is 6. So the foot of the ladder is 6 feet from the wall. That bottom part of the triangle is 6. And then the last little tricky part is the ladder reaches a height of 15 feet on the wall. So that's not saying that the ladder is 15 feet long. That's saying that the top of the ladder hits the wall at 15 feet high. So that means the height of the wall is 15 feet. And we are looking for an angle, the angle the ladder makes with the wall. So we're looking for this angle right here. So as always, we have 3 things. We have 2 numbers filled in and 1 variable. And it looks like we have the opposite and the adjacent side from that angle. So once again, we are working with tangent. So tangent of the angle equals opposite over adjacent, 6 over 15. And this time we do have to plug this in the calculator using our inverse properties to solve for theta. Theta equals tan inverse of 6 over 15. Make sure you're in degree mode here because it wants the answer in degrees. So plug this in the calculator. We get approximately 22 degrees, which once again, make sure the answer here makes sense. It does seem like 22 degrees makes sense for this problem. All right, so let's take a look at one more question. This one's obviously going to look a little bit trickier, but I promise it is not as bad as it looks. So we want to find this length x, and we're going to round it to the nearest whole number. So when you're looking at this big setup, right away, I recognize that there's 2 triangles here, right? Looks like there's this little triangle in here. And then even though you might think about this triangle over here, that is not a right triangle. We are only working with right triangles for now. So we're actually going to think about it, this whole entire thing, as the other triangle. So I'm going to work with 2 separate triangles. And what we're going to do here is from this little triangle, we're going to go ahead and find this side, which I'm going to call length A. And then for this entire triangle, we're going to find this whole entire thing right here, this whole entire side at the bottom. We're going to call that length B. And then in order to find x, we can see that x is going to equal the entire length B minus the little chunk of A subtracted off, right? It looks like this chunk x right here is all of B subtracting off this chunk of A right here. So the question is, what is A, what is B? Let's go ahead and set up these 2 triangles separately. So taking a look at this little triangle first, let's just redraw it on the left. So we have that little triangle drawn in over here on the left, and we have this missing side A down here. So as always, we have 2 numerical sides or 2 numerical values in 1 variable. So trying to find A here, we have in terms of where the angle is, we have the adjacent side and the opposite side. So we're going to be using tangent. So this is going to be tangent of 60 degrees equals opposite over adjacent, 230 over A. To solve this one for A, you can think of this as cross multiplying. Multiply both sides by A and divide both sides by tangent of 60 degrees in 1 step. So basically, we multiplied A on both sides, multiplied it to the left, and then divided tangent of 60 degrees to the right, and then plug this in the calculator. I'm going to round this to the nearest whole number. We end up getting about 133 for that side A. So side A is about 133. Now let's do the same exact thing for the entire triangle and solve for the missing side B. And then we'll subtract them right here in the middle, and then we will be done. So drawing the triangle, the entire big triangle outside of the triangle, we have the 230 and the 40 degrees. And then we know that we're looking for the entire side on the bottom, which is side B. And the good thing is, even though it looks a little bit different than the one that we just did, we're still using tangent because we have the opposite and the adjacent side that we're going to be referring to here in terms of where the angle 40 degrees is. So this is going to be tangent still. Tangent of 40 degrees equals opposite over adjacent. And then notice it's the same setup, right, that we just did. So cross multiply, divide both sides by tangent of 40 degrees. We get B equals 230 over tangent of 40 degrees. Plug this in the calculator, round to the nearest whole number, and we get 274. So now in order to actually get our answer for what the heck this x distance is, x equals b minus a. So just plug in our values. X equals 274 minus 133. That gives us an answer of 141. So our final answer for x here is 141. All right, so that is it for this chapter.